Yes, I think this is a very nice place to start, because the traditional conception of physics is actually full of problems. And as you said, this is not maybe so well known. It's, it looks like we've solved lots of problems, but there are actually more problems still. And I think these problems have been actually unsolved for several decades now. And so what I'm working on with David and other collaborators, I think, is really to try to kind of change the tools that we're using to address these problems. And so the main problem is that so if you think of the way physics works, you start with what we see with our experiences. So what is what exists in the universe around us, and then physics tries to come up with explanations for what we see. And so it kind of goes away from what we see directly, but it still explains all of that in terms of stuff that happens. So, if you see, the dark sky at night with the stars, you can explain that in terms of a number of things, including motion of particles, the way that light and photons work, and so on. And all of these things ultimately boil down to the same type of mode of explanation. And this is, explaining things in terms of trajectories of particles in space and time. And if you think about it, this has been the same mode since Galileo's breakthroughs and Newton's laws. We haven't really changed much that mode of explanation, because it was very successful, of course, and it had lots of great discoveries attached to it, and Maxwell's laws to describe light are also similarly phrased, and of course quantum theory and general relativity, they look very different from these first laws that I mentioned, but in regard to this mode of explanation, they are always using the same mode. They're telling us what happens. And they explain what happens in terms of other stuff that has happened or happened in the past, or maybe will happen in the future. However, there are things that you can't quite fit into this mode of explanation. That's the problem that I was referring to. And I think that's what the book is about, explaining in a number of different ways how this problem crops up and somehow requires us to change the way in which we explain things to incorporate more of physical reality. You have a lifeboat aboard a ship, and you'd like to explain why it is there. And of course, you can list the set of events that led to that lifeboat to be there since it was created. That's like a story about what happened to the boat, but you wouldn't quite explain why it's there, would you? Because the real reason why it's there is that there could be a shipwreck. A shipwreck could happen, and this particular event may never happen, but it's the fact that it could happen that explains why that lifeboat is there. And that is a counterfactual. And that's the kind of stuff that we need to expand on the mode of explanation that we currently have. Yes, I think this is an aspect of this problem that I'm talking about, because in theoretical physics, we maybe don't quite acknowledge that much, at least in everyday chats. But we have a problem that we have a really good, at least we think we have a really good picture of these laws of motion. So we've got quantum theory and general relativity. They both work as far as we know. They don't quite go, they're sort of in disagreement with each other, but they work in their respective domains, and we are fine with that. But there is this problem that, of course, we have to give some initial conditions for these laws of motion to unfold. And usually, as you said, you want to explain what you see now in the universe in terms of what used to be there at the start of the universe, or perhaps at the end of the universe. There's already an ambiguity, because the laws of motion have this nice symmetry that they are reversible, so they look the same in the forward and backwards direction. But let's say, supposing that we just focus on the initial conditions as explaining what's happening now, then these initial conditions look a bit arbitrary in the sense that we don't have a watertight good theory of why we should have these particular initial conditions as opposed to others, other than the fact that we know that we want to explain what we see now. But of course, that's not quite, it's a bit ad hoc as an explanation. It's not a very satisfactory one. And so I think it's quite a kind of uncontroversial statement that physicists are not so happy with the way in which the theory of initial conditions is formulated at the moment. There are a number of them. It's hard to imagine ways of testing them, for example, and also from the explanatory point of view, they have various gaps. And so the question is, should we perhaps try to change the mode of explanation? Should we go out of this paradigm of explaining everything in terms of this Laplacian view, that everything boils down to trajectories and initial conditions, to explain the initial conditions themselves? And so that's one kind of open question. And I think the kind of work I'm doing might suggest one way of going about solving this problem. But it's undeniable that there is a problem. So it's important to kind of take that on board. Yes, I think it's quite nice that, as I said, this is a fact of the most beautiful explanations we have of the physical world, that they do go beyond what, strictly speaking, just what exists. Because, I mean, that's part of what makes something a theory explanatory, right? Because it refers to things that are not directly accessible or observable, and so on. And counterfactuals are one of these elements that an explanation can use to provide a richer underpinning for what we see in physical reality. So there are several counterfactuals already in the theories of physics. It's just that we don't have them, exploited or used in the full power. So one example is the world of the laws of thermodynamics. I think this is one good example to start with. The laws of thermodynamics, if you look at them, they are not phrased. They are an exception to the rule I said earlier. They're part of the traditional physics, but they're not phrased as laws of motion. They're about forbidding things. So they're about saying it's impossible, for example, to build a perpetual motion machine, which would be a way of kind of extracting useful energy out of nothing. So that is impossible. And the fact that it says that's impossible, although it refers to something that never happens, so it says stuff, this stuff really cannot happen, it's very useful to explain all sorts of different trajectories and motions of objects around us. I think there is this nice kind of BBC episode with Richard Dawkins facing a pendulum, where he's, saying, I am happy to be placed here, and the pendulum is actually starting from just a few millimeters away from my nose, and then it's going to move away. And I am daring to stay here because I know that when it comes back, it will not hit me. And the reason why it doesn't hit me is the fact that energy is conserved and that the first law of thermodynamics is true. Now, so this is an example of how a counterfactual, the impossibility of perpetual motion, actually has a very strong, important effect on what is allowed to happen, and therefore allows us to make a prediction. So that's how, again, there's this nice link between something that is a counterfactual, something that's about what cannot happen, how that's linked to a thing that we see in the world, which is this motion of the pendulum and the way it works and so on. Yes, indeed. And they are part of any process that leads you to explain regularities in nature in a way, right? Because if you see, well, this may be true in mathematics as well. If you see a sequence of numbers that appears to have a certain pattern, an explanation for why that is goes through wondering how that particular sequence could have been. Why is it like this and not in a different way? And so this contemplating what could have been is referring to a counterfactual, which ends up being part of the explanation for why the particular sequence is the way it is. And so in a way, I think they are part of the scientific discourse. But what I think what this new way of formulating physics that we are proposing is about is to say, well, unless you resort to them, you won't be able to capture certain phenomena in nature in a sort of exact way. And I think this is an important thing I wanted to bring in. And I guess maybe captures your interest too, because you're kind of, being a mathematician, you're interested maybe in this type of issues. Yes, I think information is the right place to start because it's, it's an interesting kind of concept because, as you said, up to some time, it was considered to be mainly part of computer science, things like before that mathematics, in a sense, sort of abstract type of things, and it wasn't quite connected to physics in a sort of direct way. Except that at some point, I think in the, kind of around the 80s, and this is part of this quantum information type of thing, as people realized, and I think David Deutsch was one of these people, that there is a connection between the sort of information processing that one can perform in a given situation and the physical laws that rule that situation. So it's the laws of physics put constraints on what computations can be implemented, and this is in a sense immediate to us now, because we know that computers are physically implemented in objects that obey the laws of physics, and depending on the different physics you have, you can have different computations being possible. And this is the most basic connection between physics and information. And then you can go on, and this is where counterfactuals come in more directly, to ask what are the regularities in the laws of physics that allow for information to exist in the first place. So then you can take the unit of information and look at a bit and say, what kind of physics allows for a bit to be to exist, to kind of be possible? And the regularities are very simple, and they are counterfactuals because they are the fact that the bit, that the object that embodies the bit, for example, a transistor that can be on or off, has two possible states. So the explanation for why information can be there doesn't go through saying this particular object is in a state, but it says this object could be in one state, 0, or it could be in another state, 1. And these two states, 0 and 1, could be copied onto another bit if you had another bit around, and so on. So there are these two properties. One is the fact that the states of the system in question can be flipped. And the other one is the fact that these two states can be copied. And these are both counterfactuals because they're about what's possible to do with this particular object. And once you realize this, it's very nice because you notice that it doesn't really matter whether the bit is realized with traffic light with two different colors, or a switch on and off, or a flag, again, different colors or different orientations. Doesn't matter, all of these details are irrelevant. All that matters is that all of these objects I mentioned have these two counterfactual properties. And so that's how you go from like all of these details that seem very different and distant from each other to one regularity, which is in common to all of these systems, and the fact that they have these two counterfactual properties. And then you can just talk about bits. And in that way, you abstract away all of these other details. And usually when this happens in physics or in science more generally, I think there's a nice regularity going on, and there's a hope to be able to formulate a law that says that all of these objects are interchangeable from the point of view of what they can do with the information. And that's kind of an implicit way of talking about information, by talking about what the objects that can contain information can or cannot do.